Complex numbers part 3. Here you're going to learn some few interesting things. We have solved the quadratic equations that have complex solutions in my previous video, but now I want us to have something of this kind. Let's say you are to find or to write, the equation whose solutions are, or whose roots are. Let's say we have 2 and -4. So if you have these roots in a quadratic equations, you know that it is because x is equal to 2 and x is equal to -4. If these are the roots, so you can just write them like this. Now, if you are having solutions and you want to move back to find the equation, it is easy then. You just have to change this to be a factor, that you take it to the other side of the equation, then also this one. So when you take it to the other side, then the sign has to change. Now, you need to expand. Just to simplify this, x times x is going to be x squared, then x times 4, that is going to be 4x, then minus 2x, then minus 8. This is equal to 0. Then the equation that you'll have is just that. So these solutions, or these roots, were the roots of this equation over there. So it is done here in a real side of numbers, that we can also have some solutions in a complex number situation. For example, you have roots now, which is I, and the other one is -I. Okay, now when you have these ones as the roots of a given equation, you know that this is x equal to I, and you have x equal to -I. So since these are the imaginary roots, we can change them to factors, that we have x minus I, then times also this one, we change it to a factor, then it's going to be x plus I. This is equal to 0. So you can just expand now. Then we have x times x is x squared, then you have xi, then you have minus xi, then you have minus I squared. This is equal to 0. So basically you can see that these are the additive inverse, that they just give us a 0. Then also that one is going to be a real number, that if we know that I squared is equal to -1, because I initially was just equal to that. So when you square both sides, then therefore this I squared is just going to be -1. So you have negative of -1 now. This is equal to 0. Then your x becomes just x plus 1 equal to 0. So this is the equation whose roots are given as I and -I. So this was end. Now you also have you are to find the equation. Find the equation that has root let's say we have 2i. Let's say we have 2i. So you are just given only one root, so you need now to be able to, because if it is a quadratic, then therefore you need to know what is the another root. Since in the previous example I gave you this one and also that one, and in our real side we got 2 roots. Now if you are given only one root in a complex side of numbers, how do you then figure it out with what is another one? So it is very wise that under complex solutions, they always go in pairs, right? They always go in pairs. So if this is the root, then we also have the conjugate of this root being one of the root as well of the same quadratic equation. So if 2i is a root or a complex root, then negative 2i, which is the conjugate of this root, is also going to be a solution. So it is always the case that when you're given one, then the additive inverse of it is also going to be another solution. So now you have two solutions. When you are given one in a complex side of numbers, it's easy to find the other one. Unlike this one, they have to give you two of them because you cannot assume that the second one is negative 4. But in a complex side of numbers, when you are given this one, then therefore the opposite of it is going to be the solution of the same quadratic complex equation. Now, what are you having? You have x equal to negative 2i, and another one is x equal to 2i. So when you do your backward substitution, you'll be having x plus 2i. Then you also have x minus 2i is equal to 0. Then let's do this function. Then you have x squared, then x times that, you have negative 2ix, then you have plus 2ix, then you have negative 4i squared. This is equal to 0. So you have this now, and let's do the simplification. You can see these ones, they cancel each other. Then you'll be having x squared, then you have minus 4, then I squared is equal to negative 1. So you'll be having negative 1 then is equal to 0. So you'll find that you have x squared plus 4 is equal to 0. So indeed, these solutions are the solution of this quadratic equation, and you can see that these are the sum of two squares. Well, let's get into this one. Let's say you have the solutions are given as, or you just have one solution, which is what? Which is 2 minus 3i. So you have this one. So you need to find another solution, then find the equation. Find another solution, then find an equation. Find another solution, and the equation. Now, it is wise that if we have this as one of the solution, then also you have x equal to the conjugate of that is going to be 2 plus 3i, which is also the solution of the same quadratic form equation that you are looking for. Now ours is to say x, then you take this one to the left side, which is going to be x plus, it's going to be x, it's going to be minus 2 plus 3i for this one. Then for this one is going to be x minus 2 minus 3i. So we have that. We just moved back to find factors if we have solutions, which is something that you do in a forward direction when we were solving the solutions from the equation. Now, what we do the expansion. Now we are going to be expanding this trinomial times another trinomial, which is gonna be longer, but avoiding mistakes, we are going to pull through. So x times x is going to be x squared. X times that is going to be negative 2x. Then we have negative 3ix. Then coming to this one now, you have negative 2x again. Then you have plus 4. Then we have a plus 6i. Then you have this one now. It's going to be plus 3xi. Then you have minus 6 I. Then you have minus 9i squared. This is equal to 0. So we have expanded this. So let's collect the like terms if there are any. Then we have x squared, this one and nothing else. They give you negative 4x. Then what about this one and that one? They are additive inverse. They are going to cancel each other. Then we have, these ones we have already used them. Then let's come to this one and this one. They are canceling each other because they are additive inverses. Then the only thing that we are left with is plus 4, which is this one, and minus 9 times then I squared. We discussed about it, that I squared is equal to negative 1. So we have that. So we have x squared, then minus 4x, then plus 4 plus 9. So this is that. Then we have x squared minus 4x. So 4 plus 9 is equal to then 13. So this is the equation that has these solutions. So it is easy this way. If you're given only one solution, then the other one is the conjugate of each of it. That means if they are complex, then it's easy to find the second factor and also the equation. Now I want us now to have what we call two complex numbers that are being added, multiplied, and divided to each other to see what is going to be the relationship of those, because we are not going to only deal with one what you call complex number. There can be two in one equation or vice versa. Now we have two complex numbers that are adding each other, multiplying or subtracting, but let's just have the format of having z. Let's say z is one of the complex number, which is a plus b I. Let's have another one, which is, let's say it's w. Let's say we have c plus di. So these are the complex numbers that we have. Let's say you are asked to simplify. What are you simplifying? You're simplifying z plus w. So which means you are adding this complex number to this complex number and simplify your solution. Now, what are we having? This is just equal to a plus bi, then plus w is this one, which is c plus di. So when you simplify this, I think it is wise to take the real parts alone and the imaginary parts to be on the other side. So real parts is a and c. So we have a plus c as the real part. We can just group them so that we show that this is just one unit. Then the imaginary part, we have bi, then plus di. So I think this one, since I is a common factor, then we can just remove it so that it is in a standard form. So if you have b and d, then times I. So you can see that when you are adding two complex numbers, you get a complex number that, which is, this is the real part of z plus w, and this one is the imaginary part of z plus w. Okay, now this is, you can see that this is just one complex number now, which is found when we're adding two complex numbers. Now you can see that the real part, they go alone on separately, and the imaginary part, they also go separately. And it is also possible to subtract them. Let's say we have z minus w, then we have to simplify that. We know that z is a plus bi, then minus, it is wise to put brackets when you're subtracting now. Then we have c plus di. So we have that. So if you simplify this, of course, you're going to get rid of brackets. Then you have a plus bi, then minus c minus di, then the complex number, the real parts stand on their own. You have that. Then therefore plus we have bi minus di. Then we can remove the common factor there, which is I. That you will end up having b minus d, then I. So you can see that even here the real parts is on its own and the imaginary part is also separated. Now let's check if we multiply the complex numbers now. So number 3, let's multiply, let's say z times w. So when you say z, our z is a plus bi, then times c plus di. So we're multiplying them, so we need to expand now. A times c, that is going to be ac, then plus a di, then we have this one now, it's going to be plus c bi, then we now have plus d bi squared. Yeah, we have that. So when you multiply these ones, we are going to get something of that kind. So if we can take the real parts and imaginary parts alone, we'll find that this one and this one is on its own, but we can now we have AC. Let's talk about this one. This one, I think this is really a real part of our solution, because you still remember that I squared is equal to -1. So which means this one must just move close to this one. So if you have dbi squared, it is the same as you have db times -1. So this is just going to be -1 db. Okay, so you have negative db or bd, doesn't matter. Then you can group them up. Then these ones you can just remove the common factor I, that will have ad, then plus cb, then I. So we can see that even when you multiply them, the the real parts, they stand separately, and the imaginary part, they also separated. Now because we need to use all the operations, why can't you then divide? Let's say we divide now. We have 4. Number 4 says let's find w over z. Okay, so w over z, it is given by w is c plus di, okay, then divided by a plus bi. So we have this. So it is very wise that this, in order for us to say we have simplified it, it must be in a form of a real part being separated and the imaginary part that is being separated. So how are we going to do that? So bit thinking, I think we need to apply a certain trick or certain method just to change this a little bit, but not changing its structure. Now, when you encounter this situation, it is wise that you multiply by the conjugate of the denominator. The conjugate of z, if z is equal to a plus bi, then the conjugate of z is now going to be a minus bi. So we need to multiply the numerator and the denominator with the conjugate of the denominator. So in other words, this is what is called rationalizing the denominator. Okay, now we are going to embark on that process, Gengok. So we have a minus bi divided by a minus bi. So we have rationalized, or we have multiplied both of the numerator and the denominator with the conjugate of the denominator, which is z. So let's do the simplification now. The simplification, we have a, we have ca, we have minus, okay, let me just start from here. We have c, we have ca Then we take this one now, it's going to be minus CBI. Then let's talk about this one now. We have ADI. Then that one is going to be minus DBI squared. Well, then that is our numerator. Then denominator is going to be, one can notice that this is just the difference of two squares, but anyway, in our complex numbers we say it's sum of two squares. It's sum of two squares, but let's just do it manually so that it comes out with sense of it. Then we have a squared, then minus ABI, then plus ABI, then minus B squared I squared. Now let's continue with simplification. We can see that once we have I squared, that becomes a real part of our solution. So which means we have two real parts, this one and that one. Otherwise, if it is just I with not being squared, that is going to be an imaginary part, because that is just a square root of -1. Now, in the numerator, we sondeza these. So we have CA or AC, then minus DB times -1. Then these ones we can just probably leave them this way, or see common factor. So CT plus, you have AD and minus CB, then I pi, all divided by this one. We have A squared, and this one is said to be our real part of it. Then we have negative B squared, then times -1. Then these ones are going to be, we're going to take out the common factor. Then I start with the positive one for some strange reasons. Then minus A. No, it is not that. These are just like terms, so we can just cancel them up because they are the same. So we just have that. Now let's continue. Let's simplify this numerator and the denominator real part. Then we have CA, then plus DB, then plus AD minus CB, then times I. Then good denominator, we have just A squared, then plus B squared. So our target is to make this whole thing to be in this format. This format, there must be a real part must be on its own, and the imaginary part must also be separated. Now we can see that it is close there because yonke lento is divided by this real part. So this real part is dividing this part, and this real part is dividing this part as well. So it is wise now that we separate them. So we have CA plus DB divided by A squared plus B squared. Okay, then we have plus, so this one is also divided by the very same denominator that we find ourselves having, AD minus CB, all divided by what? A squared plus B squared. Then there's I in that. So we can see that this is the imaginary part of what? Of WZ. Then this one is the real part. Real part of what? Of WZ. Okay, so it is good for that. Now you can see how useful the conjugate is, when especially when you are dealing with fractions, that it takes you to a very simple step. Now let's just play with these numbers, these complex numbers, so that you can get a little bit of the understanding here, terminology and the signs, the notations that are being used. Let's say you are given this P, which is one of our complex number, which is 2 root 3i, and you're given Q, which is negative 1 plus root or plus 2i. So we have these two complex numbers. These are the complex numbers, two of them. Now, if the question may say, simplify the following, giving your answer, you're simplifying now. Simplify the following, and your answer must be in the form a plus bi where necessary. Okay. Now, if number one can ask you to write down a real part of p, they're going to say re then p. So this real part of p is given like that. So real part of p is that one. Okay. Then you have that too. So if one can ask you about the imaginary part of what of q, what you do right? Think about it. The imaginary part of q. Got it. So it is that too. Then if one may continue to say what is, okay, you simplify p plus q, which is something that we've already done by variables. But anyway, we can just play around with these numbers now. P is 2 minus 3i. Then plus q is what? Is minus 1 plus 2i. So we're just adding these two things. So 2 minus 1 is just 1. Then negative 3 minus 2 plus 2i is just going to be negative I. So p plus q is just going to be this complex number 1 minus I. Now, number 4 may say write down or simplify p minus 2q. So which is of course algebra. So our p is this one, which is 2 minus 3i, then minus, which is this minus, then 2 times q. Our q is of course this one. So we can just say minus 1 plus 2i. Then finding it easy to simplify, we have 2 minus 3i minus, let's say this is going to be plus 2, then minus 4i. So simplifying this is going to be 4, then minus 7i. Done. Then if one may ask you to simplify I times p, so simple, because we have I, then your p is given by 2 minus 3i. So we can just say 2 minus 3i. So to simplify this, you have 2i minus 3i squared. That you'll find that now this is just going to be a real part of it, because once we have I squared, it is then changed to be negative 1. So you have positive 3 now plus 2i. So simplified this way, because negative 3 times negative 1 is just positive 3. So that is how we just have that. So you find that one may ask you to find, let's say we have this is number 6, and say find p conjugate of p times conjugate of what? Of q. So we need to first know what is p. Our p is equal to 2 minus 3i. Then the conjugate of it is what? Is 2 plus 3i. Then our q was given as minus 1 plus 2i. Then the conjugate of it is going to be minus 1 minus 2i. So what we're going to do now, we're going to multiply these numbers. Going to multiply this conjugate. Now what we have this is equal to, you have 2 plus 3i times negative 1 and minus 2i. Then this is going to give us 2 times negative 1 is negative 2, then it's negative 4i, then we have negative 3i, then we have minus 6i squared. So in simple, we have negative 2, then plus 6, then negative 7i, then the answer is negative, that is just 4 minus 7i. Okay, so we just have those things, and the rest game you can just continue with your classwork to find p times q conjugate, then also at number 7, which is you are going to find a real part of q conjugate divided by just p. Okay, now you can just do them at your spare time. So that's basically that. So there's a lot together that you can learn on these things and stuff like that. Now let's say we have z, which is given by a plus bi, that we know that the conjugate of it is equal to, the conjugate of it is basically equal to what? The conjugate of it is basically equal to z, with z conjugate is equal to a minus I. Now let me say let a be equal to the real part of z over z conjugate, and b being equal to the imaginary part of z divided by z conjugate. Good to show that a squared plus b squared is basically equal to 1. So what do you do? So the idea is to play around with these numbers, and of course they are sending you to first find z divided by z conjugate, and no z divided by the imaginary part of z divided by z conjugate. So it's going to be a long thing to do, but let's get along. First of all, z divided by z conjugate is equal to what? Because that's the first thing that you need to discover. Z divided by z conjugate, our z is given by, you have a plus bi divided by, the conjugate of it is a minus bi. Okay, then we know how to simplify this. We have to multiply by the conjugate of the denominator, which is actually z, in short. So we have a plus bi divided by a plus bi. Okay, so when you do the expansion, you'll find that you have a squared, then plus a bi, then plus a bi, then plus b squared I squared, all divided by what? The denominator, you can see that this is just the difference of two squares, which is going to be a squared then plus b squared, in short. Otherwise you can play around with this expansion thing. Then what do? We know that numerator, we have two real parts, which is this one and that one. Then we have a squared, then you have minus b squared, because this one will become minus b, right? Then on the other side we have these ones. This is just 2abi, okay, then divided by a squared plus b squared. But now I need to put it in a sense that the real part is on its own, then the imaginary part is on its own. So that what we can do, you have a squared minus b squared, all divided by a squared plus b squared, then plus we have 2ab I divided by a squared plus b squared. So it is wise that this one can be just put in this way, so that you can see that this is the real part of what? Of z divided by z conjugate. And this one is the imaginary part of z divided by z conjugate. Okay, so you'll remember the question that's saying we need to show that a, which is the real part of our z divided by z conjugate, plus b squared, which is the imaginary part of our what? Our things. So which means now our a is equal to, basically it's what? To a squared minus b squared over a plus b squared, because this is our real part of it. Then which means our b is 2ab, then we have that plus b squared, right? This is our b, which is the imaginary part of our solution. Now when you say this is squared, we need to have these are being squared, right? So we are now proving that these two things are equal to 1. So you have a squared minus b squared all divided by what? This plus that, all that is being squared, then plus this one, which is 2ab all divided by that. Okay, yes, all divided by that. Let me just take these ones out. Then is equal to what? And then now it is wise that numerator, you can see that you have what? You have a squared, then minus, yeah, we have a squared. We are expanding these things now, né? So we have a squared, no, it's gonna be a to the fourth, then this times 2, then it's gonna be minus 2a squared b squared, okay, then plus, then negative b squared, that is gonna be plus b to the fourth, then all divided by a squared plus b squared all raised to 2, then plus on the other side we have 4a squared b squared divided by a squared plus b squared all raised to 2. Now we can see that since the denominators are the same over there, we can just add the numerators. So we have a to the fourth, then minus 2a squared plus b squared plus b to the fourth, then plus 4a squared plus b squared all divided by a squared plus b squared all squared. Okay, then simplifying this and that, these are like terms, so we can just add them together. We'll find that we have a to the fourth, then and plus 2 and that, then plus b to the fourth all divided by a squared plus b squared all over all divided by that. So I think this one is factorizable, and it is factorized in a form of, we have a squared plus b squared times a squared plus b squared. That is going to be a squared plus b squared to the denominator. Then we can also expand this way so that it's going to be clear when they cancel each other. So you can see that this cancel that and this cancel that, then you just get 1. So it is indeed shows that a squared plus b squared is just equal to just 1. So it's just a matter of playing with numbers here and get along with what is required. Okay, so I would like to take you through in the next video for the next interesting stuff. Don't go away.